So hello dear students. So now we are going to proceed to the next part of our endeavor in understanding one-dimensional uniform motion. And now today we are going to discuss in this video a one-dimensional uniformly accelerated motion. So that you can say that the velocity of the object is changing in one dimension, but it is uniformly accelerated. So it is changing, the velocity is changing at a constant rate. So let us start with accelerated motion, and we talk about a one-dimensional uniformly accelerating motion today. So what is acceleration? So let us define acceleration, and there are two types of acceleration. One is the average acceleration, which is defined as a average, and the other one is instantaneous acceleration, which is defined as a instantaneous. So let us talk about the first one, which is average acceleration. So let us say if an object is moving and it is moving and it is changing its velocity, its initial velocity was vi and its final velocity was vf. So the change in the velocity is vf minus vi. So the total change in the velocity from the initial point to the final point is vf minus vi. So that is the change. And when you divide it by the total time taken from the initial position to the final position, then you get the average acceleration. So it is Vf minus Vi over Tf minus Ti. So this is the average acceleration. So you can say in one dimension, if an object moves from here, it has got some initial velocity Vi, and after some time, at time t is equal to Ti, and after some time, it moves ahead and its velocity now becomes Vf at time Tf. Okay, so in that case, the average acceleration during the complete motion from this point to this point, in that case, average acceleration would be Vf minus Vi over Tf minus Ti. Now let us talk about instantaneous acceleration. So let us say if the velocity is changing. So let us say the object is here and it is moving and its velocity is changing. Now let us say the change in the velocity delta v has taken place for a very short interval. For a very short interval, the change in the velocity is delta v, and that interval is delta t. So you divide it by delta t. Okay? And then you take the limit that delta t is tending to 0. That is, there is a change in velocity of this object delta v in time delta t, and the duration of this time delta t is very small. It is infinitesimal. It is actually tending towards 0. So in that case, when you take the limit that the change in the velocity that you are measuring for that object is basically at a very small instant of time, very small fraction or period of time, which that period of time is tending to 0, then in that case, when you take the limit of delta t tending to 0 of delta v by delta t, then you can represent it by this notation dv by dt. So this is the instantaneous acceleration, and this is the acceleration that is at a particular instant. So basically this instantaneous acceleration, the concept of instantaneous acceleration is relevant when we are talking about non-uniform acceleration. That is, at each point in time that there is certain value of acceleration, and that value of acceleration is changing for different time periods. So it is changing, and that change is happening at continuously at different time periods. So at each instant of time, you have a certain value of acceleration, which is defined like this. So there are two different quantities, A average and A instantaneous. and A average and A instantaneous, both of them are what you can say are vector quantities, because velocity is a vector quantity, so acceleration also becomes a vector quantity. So these two quantities are vector quantities and they have a direction. Okay, so let us talk about uniform acceleration for the time being, and we are going to talk about uniform acceleration, and in that case the acceleration is not changing with time, so you can say that the average acceleration is equal to the instantaneous acceleration, because the acceleration is not changing with time, so whatever acceleration is there over the total duration of the motion of an object is also same as the instantaneous acceleration at one particular time. So you can say for uniform accelerated motion, A average is equal to A instantaneous. Okay? So I think you have understood the basic concept of acceleration. Now we will go to the kinematics of the uniformly accelerated motion. So we are talking about uniformly accelerated motion, and when we are talking about uniformly accelerated motion, there are actually four fundamental equations that you should know, which govern the motion of an equation of an object, you can say, and in a uniformly accelerated case. So those four equations are known as equations of motion. And from there, if you are talking about a uniformly accelerated motion, you can calculate quantities if you know certain other quantities. Like if you want to calculate the final velocity, if you know the initial velocity and the acceleration and the distance covered, then you have an equation to do that. Similarly, if you want to calculate the final velocity, if you know the initial velocity, acceleration, and the time taken for the complete motion, then in that case also there is a certain equation you can use to calculate that. So there are some unknowns and some known parameters in a given equation, and then you use that equation to calculate the unknown parameters from the known parameters. So there are four kind of equations I will write down here. Therefore, let us say actually there are uh, few variables. So you can say u is one variable that is called the initial velocity. Okay, at time t is equal to 0. Similarly, you have another variable which is v, which is final velocity. So this is the velocity which which actually is attained by the body at time, at time t. So an object starts moving and it is having an initial velocity u at initial time t is equal to 0, and at a final time t it attains a velocity v, which is the final velocity. Then you have the constant acceleration, and also you have the displacement s during that time period. So it is the displacement during the time interval So these, you can say, these are the four basic variables. All of them depend upon time. So time is another variable. So in total there are five variables including time. So there is u, v, a and s and the time t. So there are actually five variables here, and you have a set of four equations which actually relate these five parameters. So one of the parameters is unknown and it is dependent upon the rest of the parameters, and you can calculate the unknown from the known parameters. So the equations I will write down here. The first one is v is equal to u plus at. This is the velocity time relation. Then you have s is equal to ut plus half at square. This is the position time relation. Then you have v square is equal to u square plus 2as. So this is position velocity relation. And the final one is s is equal to half u plus v times t. So this is the position average velocity relation. Okay? So you have to understand the context in which these equations are actually used. See, if you are using equation 1, then it is the equation that you use when displacement is not involved. So you don't have the displacement, but you need to calculate velocity, the final velocity, or some other quantity. So similarly, equation 2 is when the final velocity is not known and it is not involved. You don't even want to know about it. Okay, then equation 3 is for position. It is when the time is not known and it is not involved. You don't need to know the time at all. Either you don't want to calculate it and it is also not given to you. And equation 4 is when acceleration is not involved. So you don't know the acceleration, but you know the initial and the final velocity, and you want to know at what particular time, in a given time, what is the final, what is the total displacement. So let us try to derive these equations. Okay? So let us start. So let us derive the first equation. That is u is equal to v plus at. So let us derive this equation graphically. Okay? So graphically, if you know, if you plot time versus velocity graph, so in that case, it is a straight line if the motion is uniformly accelerated. So you can say why it is uniformly accelerated motion in this case, because you can say in equal interval of times, the velocity is changing by equal value. So if you say this is the time here, there's an interval here, and there's an interval here. in both the cases, the change in the velocity is the same. So that means if a straight line is representing a uniformly accelerated motion in which the rate of change of velocity is constant. So it's a straight line which tells you that the rate of change of velocity is constant. So it represents a uniformly accelerated motion. And in that case, uh, what would be, you can say, acceleration? It would be the slope of the graph. It's the rate of change of velocity. So the slope of the graph tells you delta v by delta t will give you the slope of the graph. As you know from the graph and the concept of the slope of the graph, the rate of change of velocity is the slope of the graph in the vt diagram. So delta v by delta t is actually the slope, and the slope is basically change in velocity divided by change in time. So it would be equal to the acceleration by the definition of acceleration. Okay, so A would be slope. Okay, so A would be the slope of the graph. So A would be change in the velocity, that is v minus u, over change in time, which is t minus 0. So let us say it started at time t is equal to 0 and it reached at this time t at the point here with the value v here. So the change in time t is equal to 0 to time t is the change in time, which is t minus 0, and the velocity is at this point, if the velocity was u and the final velocity was v, so v minus u over t minus 0 will give you the acceleration. So from here, if you simplify, so a becomes at becomes equal to v minus u, or if you rearrange, it will give us u rather v is equal to u plus at. So have you understood this? This is how the first equation is derived graphically. So let us move now to the second equation. So the second equation is S is equal to ut plus half at square. So this is the second equation. So again, if you remember, the displacement is given by the area under the velocity time graph, if you remember that. So let us say if you have a velocity time graph here, okay, so this is the velocity here on the y axis, and you have the time on the x axis. So you know that displacement is the area under the velocity time graph. So let us say this is the time t and this is at time 0. So the area would be the area of this, you can say, this quadrilateral, which is basically the area of this rectangle plus the area of this triangle. Okay, so this is the total area under the graph from 0 to t, and actually the velocity is changing from from u to v. Okay, so from here to here, the velocity is changing from u to v, and the time is changing from 0 to t, and then you have this area from here to here. The area under the graph is given by the area of this rectangle plus the area of the triangle. So what is the area of the rectangle? The area of the rectangle is just u into t. This is the area of the rectangle, that is length into breadth. So the length is t and the breadth is u. From 0 to u, the breadth is u. So this is u and this is the length, which is t. So this is the area of the rectangle. And then what about the area of the triangle? The area of the triangle is half. base into height. So what is base? Base is basically t, obviously, and the height is u minus v. Okay? So this is the formula that you get when we are talking about s from the velocity time graph. So if from the velocity time graph, if you want to calculate s, this is what you get. Now you know that area, acceleration as defined is u minus v over t as we have defined. So you can say, you can divide here by t and multiply by t. Okay, so you can divide here by t and multiply by t. So what do you get then? You get s is equal to ut plus half t square into uv by t, which is equal to a. So finally you get this formula that s is equal to ut plus half a t square. Okay, so this is how you get the second formula. Now let us go on to the next formula. That is v square is equal to u square plus 2as. Okay, so now again, as displacement is the area under the velocity time graph, so you can say you have a velocity time graph here and you have a uniform velocity time graph, that is uniform acceleration. So the area under this graph is the area of this trapezium. Okay, so what is the area for trapezium? It is basically S area is half sum of the parallel sides ठीक है into height. Okay, so this is the area, so the sum of the parallel sides. So this is one side which is parallel to the other. So the sum of the parallel sides is u plus v simply. So this is one parallel side, its length is u, and this is the other parallel side and its length is v, as you can see. So the sum of the parallel sides is and what about the height? So this is the height. Okay, so this is t. Okay, so in this case you can see area is half u plus v into t, and this is that area under the curve, so this should be equal to the displacement s. So what is t? From the first equation you know that u is equal to v is equal to u plus at. Okay, so you can calculate t from here. It is v minus u over a. So this is equal to t, as you know from this equation. So you can substitute it here. So you get half u plus v into u minus v over a. Okay, so you're getting this. Now from here, if you rearrange, you get, after this rearrangement, 2as is equal to u square minus v square, or you can say v square is equal to u square plus 2as. Okay? This is how you get this equation. So we have calculated, actually we have done all the three equations, and what about the fourth equation, the final equation we are talking about is, the final equation is S is equal to half u plus v into t. So this is the final equation, and so this can be this can be obtained very easily. Okay, so basically again displacement is the area under the velocity time graph. So you have a time here, you have velocity here on the y-axis, time on the x-axis, and then you have a straight line because it is uniformly accelerated motion. And then you want to calculate the area from here to here. This area you want to calculate. So there are different ways you can calculate this area. One of the simplest way is v and u here. So you have a u here and a v here. So basically, again, this formula is, we have already seen this formula earlier when we were calculating the third equation. So it is basically area of the trapezium which is basically sum of the sum of the parallel sides into height. So sum of the parallel sides is basically u plus v. You have u here, which is one parallel side, and v the other parallel side. So half u plus v into t. So you get this equation here. S is equal to half u plus v into t. So this is how we get all the four equations here from graphical method. And you should know that the graphical method is recommended in the CBSE 11th class physics. That is, you need to derive these equations using the graphical method and not calculus based method. So you can use these graphical methods to calculate the four fundamental equations of motion for uniformly accelerated motion. And that would, now you can, if you can do the alternative method also, that is the calculus based approach, and that would be another thing that we will do later on. So right now we are only doing the CBSE approach, in which you need to calculate or derive these equations using the graphical method. Okay.